Okay. All right, so window. Here we go. Let's do entire screen. All right, here, that's good. Okay, so I think we're good now. All right. So can everybody see my screen okay? Just leave a message in the chat if there's an issue. Okay, so tonight we're going to go over some approximation theory, and we're going to look at a few different techniques. I'm going to give you a little introduction to it so that you kind of get the idea, and then we'll get into some of the more important techniques. So approximation theory is a branch of mathematics that deals with approximation of functions by simpler, more manageable functions. Make sure there's nothing in the chat real quick. Okay, looks good so far. I assume everybody can see the screen okay. Okay, so this has a crucial role in various fields: numerical analysis, engineering, computer graphics, and scientific computing. And then I'll just start with a little bit of an example, trying to approximate one function by another. So what kind of motivates this stuff? So here I've created a basic function, sine x plus cosine x. And I've plotted it with some various points between 0 and 2 pi, 100 different points. And then I'm going to just pick a simple function, x. It might not be the best function, but just to give you an idea of what we're trying to do here. And then I've added some code here so that we can see what that looks like. All right, and you can see here from this graph that we have our function. Our sine x plus cosine x was just this curve here. And then we're trying to approximate it by g of x equals x. Not a very good approximation. So that wasn't a great function to choose. And we'll get into some methods tonight, or today rather, for you guys that will help to approximate that better. All right. So here's some basics of approximation theory. We have an approximation. This is an estimate or a simplified representation of some complex function or data set. The approximant is a simpler function that's used to approximate the more complex one. And approximation error is the error, which is the difference between the original function and its approximant. So if you ever studied like sequences of functions, you might use the error to determine how big your epsilon needs to be. Okay, and some different types of approximations that we'll look at. The first will be polynomial approximations. Next, we'll look at some interpolation, which is approximating between points. We'll look at very standard least squares approximation and some of the variations of that. And then we'll end with some splines and how we can use those to approximate functions. Some key concepts that we'll discuss and look at are convergence, uniform convergence, and approximation orders. All right, so before we get started, let me make sure there's no questions in the chat, and then I'll continue with the approximations. Okay, great. All right, so I'm going to start just by introducing some polynomial approximations. This is a good place to start. It gets you the idea, and then it adds a little bit of more like pure mathematics for you to think about in your free time. So polynomial approximations are a fundamental aspect of approximation theory. They're widely used due to their simplicity and effectiveness. And the main reason that we talk about polynomial approximations comes from something called the Weierstrass approximation theorem. The Weierstrass approximation theorem states that for any continuous function f of x on a closed interval ab, and for any epsilon greater than 0, there exists a polynomial p of x such that f of x minus p of x is less than epsilon for all x in that interval. So basically what it's saying is that we can approximate continuous functions with polynomials, right? So that's a really nice thing because we know how to work with polynomials, especially when it comes to things like calculus. You know, we have lots of nice rules for integration and derivatives for polynomials, and this allows us to approximate continuous functions. So here I've created a little example of the Weierstrass approximation theorem. And I'm just using the mathematics library NumPy in Python, and then a plotting library matplotlib so that we can see what's going on. So first I start with a complex function, and by complex I don't mean complex valued, I mean it's just complicated, right? There's two different synonyms for that word. So I call that f, and this is just some notation that allows me to define a function in Python, this lambda here, and then x would be my variable, and then I define what the function does. So it says square x, use the NumPy library to take sine of x, and use the NumPy library to take the exponential of x, and then add those all together. Okay, so that's the continuous function that I want to approximate. And then I choose my interval, AB, so that's 0 to 2 pi, right? I've got sines and cosines and exponentials in there. So that's a good interval for that. And then after that, I choose my epsilon value, 0.1. Now I want to find a polynomial that will approximate this function within this epsilon. Okay, so the first thing I did was I chose the degree of my polynomial, in this case 2, right? And then I'm going to go ahead and plot it. So I've created a bunch of points, just 10 points actually. And then I'm using the polyfit function, which you can see just helps us to take a polynomial and fit it to our function. So it's the variable x. It's going to fit it to our function f of x that we created here, and it'll be of degree, whatever degree I've specified here. And then p of x will be the polynomial, one-dimensional polynomial of that function. Now, first I'm going to show you that the degree 2 is probably not a good approximation, so we might have to go higher for this particular function. And what I've done is I've created some figures here to plot this, and so let's just see what that looks like. All right, so here I have my original function in blue and my approximation in orange. So if I try to approximate my function with a just degree 2 polynomial, it's not doing great, right? So if we up the degree, we might get a better approximation. So let's see what happens if we go to 3. Okay, degree 3 is doing a little bit better. You can see that it's getting closer to the original function. It's got these little curves in it, so maybe we'll try one more with 4 and see what happens. Okay, and 4 is really good. And you can see as I'm increasing the degree of the polynomial, it's becoming a better and better approximation. Now, just to kind of experiment and see what happens, let's see what happens if I try to increase the degree too high. So let's say I make it, I don't know, a polynomial of degree 9, for example. Okay, so that one's okay. It's actually almost a perfect approximation of the function if I use degree 9. But if I use degree 90, let's see what happens. Probably take too long. Okay, so in this case, it's getting a better and better approximations. But sometimes if you increase the degree too much, you can actually start going in the other way. So I think maybe 5 is just as good as anything higher. So that would be our sort of minimal degree to get a really within that idea of how this Weierstrass approximation theorem works. We have a continuous function here, and then we want to approximate it very close with some polynomial. And by the theorem, it says that polynomial exists. If you're interested in seeing why that's true, you can look up the proof in any kind of real analysis book to get a better understanding. Okay, another really useful tool for approximating functions using polynomials is Taylor series, which you guys have all seen from your calculus classes. And you know that Taylor series is, a polynomial. It's like an infinite sum of terms, but you truncate those polynomials. We've seen that in previous lectures. And so I just wanted to give you another, feel for this, how we can use different types of polynomials to approximate functions. So again, I'm using NumPy and Matplotlib. And I have a function here, f of x equals sine x. It's not really a complex function because it's, we have a closed form representation of it, but in the real world, it'll be a complicated sort of function. You might have to approximate with polynomials. And then I'm going to choose a point for my Taylor expansion that I want to approximate. In this case, I'll use pi over 4. Next, I'm going to calculate the Taylor series expansion around my point, or around A, right? A is my point. And then again, it's similar. N is the degree of my Taylor polynomial, so I've truncated the terms after that. As we saw before, wherever you truncate your Taylor polynomial, the next highest degree term is how you approximate the error of the approximation, right? That gives you a way to bound the error of the approximation. So don't forget all the other stuff we've learned, and you can apply it in these situations. Again, I'm taking 100 values between 0 and 2 pi, and then I'm going to make a range of zeros. And here I'm just creating the Taylor polynomial. So for k in range n plus 1, in this case it would be 5, I'm going to take t, which is my 0 vector here, and I'm going to add to it these each term of the Taylor polynomial, which should look familiar to you, right? So we have f of a divided by k factorial in this case. You might usually call it n factorial, and then times x minus a to the k. So that's the common expression that we all know for Taylor series approximations. And then finally, I've just made a little bit of a figure here so we can see what's going on, so it's not just all symbolic. All right, and here we have the original function in blue, and then the Taylor series approximation. So what's going on here? Well, this is actually illustrating something that you've learned about before, and that's, the radius of convergence, or, we're in a small neighborhood, it does really, really well around pi over 4. But as we get outside of that neighborhood or interval, we don't get so good of an approximation. So it's doing really well here, but then outside of that, it's not great. So that illustrates something that you know about, and you should think about kind of more deeper, that there is a radius around the point A that we can look at where the approximation will be better, and then outside of that radius, the approximation maybe is not so good. Okay, so that kind of motivates what we want to do next. I'm just going to talk about a few interpolation methods, and I'll introduce them in a very simple kind of way, and then we'll get into the mathematics of them to kind of get a much deeper understanding of them. So let's do that. So interpolation methods are used to construct a function that passes through a set of given data points. So in this situation, you're usually given a whole bunch of like XY pairs, and you want to create a function that will predict the values in between the pairs, right? Or in between the points. And if that doesn't make sense, hopefully it will as we move forward a little bit. There's a lot of different types of interpolation methods. But for now, I'm just going to go over the Lagrange interpolation. And this is a method for constructing an interpolated polynomial that passes through a given set of data points. It gives us a polynomial. So it might not be a polynomial that we're using to interpolate, but in this case, and most of the cases that we'll look at today will be also polynomial in nature. And this uses Lagrange basis polynomials to achieve this. So you're probably asking, well, what's Lagrange basis polynomials? And we'll get into that, and we'll get into that a lot deeper here in a minute. Another interpolation method that we have at our disposal is Newton interpolation. So this is another approach to construct interpolating polynomials, and it uses what are called divided difference tables to simplify the process of finding the interpolating polynomial. Oh, okay. Seems like we have a question here. I'm not sure what happened. I know I've sent them twice. So yeah, the email should maybe check the email. I'm not sure. But I've definitely sent through email both lectures and problems for you to work out. Yeah, so I'm not sure what's going on with that. You'll have to talk to your co-instructor about that. Okay, so so if there's no more questions, I'll go ahead and continue. Yeah, I have, all of this also for tonight, and also some materials for you to look at here too. So I've definitely been sending them. I'm not sure if there's an issue, then please tell your co-instructor, and she can let me know, and we can see what's happening. Maybe it's like going to spam an email or something. I'm not sure, but yeah, it's a good question. All right, so let's go ahead and get into this a little deeper. I introduced the two techniques that we'll look at, so I want to talk about them a little more and sort of understanding what's going on. So Lagrange polynomials are a method for interpolating polynomials that pass through a set of given data points, like I said, and this is kind of a simple and easy way to approximate a function using a polynomial. So you understand that we're using these polynomial techniques because we have the Weierstrass approximation theorem, which says that if we have a continuous function, we can always approximate it by a polynomial. So that's why we're kind of exploring these paths. In this lesson, we'll explore the concept of Lagrange polynomials, and we're going to learn how to construct them for interpolation. Okay, just to reiterate. And just to reiterate again, I'm trying to understand interpolation a little bit more. I'll just say it again. It's the process of estimating data points between discrete data points, right? So we have a bunch of points, and we want to sort of estimate what kind of function is making those points. And this is something that shows up a lot in math, engineering, and computer science, to approximate functions or curves that pass through those points. So this is a pretty valuable tool for interpolation whenever you want to do any kind of interpolation, right? Okay, so the first thing we should talk about are the Lagrange basis polynomials. So these are the building blocks of Lagrange interpolation, and they're used to construct the actual interpolating polynomial that passes through a set of given data points. Okay, so this is how we'll build the polynomial that'll help interpolate the function that's being defined by our data points. And here's the definition. Okay, Lagrange basis polynomial, which we'll call L sub I of x, for a given set of data points, so these are our pairs, x0, y0, x1, y1, all the way up to xn, yn, is defined as this. So let's kind of pick this apart a little bit and see what's going on. So Li of x is going to be, so this is a function of x, as you can see here, and you can see that it's indexed by I, right? So we'll start with j goes from 0 to n, and we do not want j to be equal to I, otherwise we would be dividing by 0, right? And then we're going to take products of these. So the way to kind of think about it is when you did polynomials in your algebra class, you would find the roots of those polynomials, and then the polynomial could be seen as a product of roots, right? So that's what this big symbol here, it's a product, and it's supposed to be like P for pi. You know, in some languages, this is the letter P. And so that's what it's supposed to remind you of, P for product, P for pi. And we'll multiply all these together. So remember that the indexes of these, x0, x1, so that's what's going on with these j's and i's, right? And so the 0th one would be a fixed x0 here, and then we would iterate through the j's. So x0 minus x1, x0 minus x2 in the denominator. And then the numerator has the variable x, and then the j's again. So it would be x minus x0. Well, x minus x1, x minus x2, you know, for whatever I we're choosing. And so you can see that we get one of these for each I in our ordered pair. So here we have 0, 1, 2, all the way up to n. We'll get a Lagrange basis polynomial for each one of those i's, right, following this formula. And they're pretty cool. They have this property that the ith one, if I plug in xi, well, what happens, right? If I plug in xi, if that's the input for this function, then I get xi minus xj, and then in the denominator, I get xi minus xj. So that's something over itself, that's 1, and 1 times itself is 1, so that's 1. And then when I plug in xj, whenever I is not equal to j, right? If I plug that into the variable of the function, it's 0, right? Because the numerator is 0. So it has this really interesting property, and it's kind of like a basis. If you remember from your linear algebra class, you know, the basis vectors of R3 or R4, R2 or whatever are just vectors where it has zeros everywhere and 1 in one place. So it's following this sort of idea from that. So this is a pretty important thing to know. Now, how do we construct a Lagrange polynomial, right? So if we have a Lagrange polynomial that goes through or to construct this so that it goes through all of the data points that we have, we can use this formula. Right, so remember that, well, I wrote it here. So P of x, again, this is a function of x. Now this is a sum, right, from I equals 0 to n. So it's not a product, it's a sum. And we take the yi, right, so we're summing over all of the y coordinates of those ordered pairs. Remember, those were xi, yi, so there's a y coordinate. And we multiply that by the ith basis polynomial. And now you can see really why they're calling it a basis, because this should remind you from your linear algebra class as a linear combination, right? So it's like a linear combination of basis vectors, and then this gives us a polynomial. And what's n here? So n is the degree of the polynomial. So we sum up to whatever degree we want. And typically we want to use the number of data points minus 1, right? Because after that, it doesn't make a lot of sense. And why is the function value at the point xi? So if those are ordered pairs, as we saw up here, you can remember that from algebra, y is equal to f of x. So this could be x0, f of x0, x1, f of x1, all the way to xn, f of xn. So that's what I mean by that it's the function value at the data point x. And then I, as we saw, is the Lagrange basis polynomial for xi, or the ith Lagrange basis polynomial. So this will interpolate the data points themselves exactly. And then in between the data points, it's going to give some kind of curve that's a polynomial. and the degree of that polynomial will be n, and that's going to be the approximation that we're using to try to find a good approximation to our function y, or f of x, in this example. So that's the idea here behind this. So let me go through a little example here how we can do this. Again, we're just using the NumPy library and matplotlib for plotting. And I have some data points here, right? So I'm going to just have, so I have my x data is 0, 1, 2, and my y data is 0, 1, 4. So if if you're particularly astute, you probably realize this is y is equal to x squared in this case, but it's a good place to look at and start with. And then I've just defined this Lagrange interpolation function. Okay, so let's go through how this works. This is going to take in as a variable x, and then our x data and our y data. We need a variable x when we define the functions, right? So the n will be however long the x data is, or the y data you could have used here as well. And for this one, I'm just starting with a counter, right? So result equals 0. And if you look at the bottom of this, you'll see result plus equal. So it's going to increase this by some number called term, right? And you'll see what that is as we go through this code. And so for I in range n, which is going to be the length of our data, which is however many points we have. And for j, we have a term, which is the y value data of I. So the first one will be 0, right? Y0, and that's 0. The next one would be y1. Y1 is 1. And the next one would be y2, and y2 is 4. And then we add another loop for j in range n, and we don't want I equal to j, remember. So if I is not equal to j, we'll take our term and we'll multiply it. We'll multiply these expressions together, right? And then we'll sum them up, right? So I have my y value multiplied by the ith Lagrange polynomial, and then we sum those all up and return the result. And you can see this expression here, or this equality here rather, is exactly matching what we had above, but it's just written in programming notation. And then we'll add all those up, and that'll give us the Lagrange polynomial. And so once we have a way to code our Lagrange polynomial, we can do our interpolation, right? So I'm going to start with 100 points between 0 and 2 for our x interp, and then our y interp is going to be our Lagrange polynomial function. Why did I choose between 0 and 2? Because you look at the x data, it's between 0 and 2. So I'm going to take 100 points in this interval here between 0 and 2, and I'm going to plug those into my Lagrange polynomial for the x value and see what kind of polynomial we get. And then finally, we'll plot all of that just using some plotting libraries and some plotting points. So I'm going to plot my x data, y data, that'll be our points, and we'll color those red with a circle marker style. And then I'm going to plot, right? Scatter will give me the points individually, plot will give me a curve, and this will be our Lagrange interpolation curve that's trying to interpolate the function that goes through those points in a polynomial fashion. And then just some x label, y label, a title, and then I'm going to plot a grid. So let's go ahead and see what this looks like. All right, so there we go. So you can see the points are the 3 data points we had that lied on 4, 2, 1, 1, 0, 0. And then I just chose a lot of different points between 0 and 2 and plotted those, and that's my Lagrange interpolation polynomial. So if we guessed that our function was x squared, in this case, the Lagrange polynomial did a pretty good job of approximating what looks to be x squared. Yeah, so, if you look here, about 1.4 is the square root of 2, and we know that the square root of 2 squared is 2. So it looks like it's doing pretty good if that was what the function was. It might not be. It might be that the next value, if we went up to x equal to 3, maybe it jumps to 25 or something, right? But for these, it seems like it's a good guess to say that the polynomial that we're getting is x squared. So that's how Lagrange interpolation works. Like I said, I'll give you all of this information in some notes so you can really look at the algorithm. I'll give you some problems to try, and you can work these out. So that's a good place to start. All right, I'm going to do another one here. I think I just did one more just so that I like to, make sure that you see it a couple times to get the ideas in your mind. So let's go through this. I'll go through it a little faster, but I'll go through it. So in this case, my x data is 1, 2, 3, 4, but my y data is a little different, right? So it's 0, 1, 0, 1. So that's a little bit different than an obvious guess for x squared. You might, from looking at the first two, think that, oh, y is just x minus 1. But then when you get to the third one, that's not true. So who knows what it is, right? It could continue as 0, 1, 0, 1 forever. It could change. We don't know. But what we want to do is find a polynomial that goes through those points and interpolates a function that goes through those points. And again, I'll use my Lagrange polynomial function. And it's just the same thing I did earlier. It's going to take as input our x variable, our x data, our y data, and we'll define a length. That'll be our n, however long our data is. Like I said, you could use x or y because we have to have the same number of x values and y values. And then I just start a counter here, result. And so for I in range n, my term will be the yi. So that's the same yi that I'm using here, right? And those are the yi's that are in these ordered pairs. Okay, so that's my y data I. And then for j in range n, if I is not equal to j, I'm going to take my term, my yi, and multiply it by the ith Lagrange polynomial, which is x minus xj. And that's why we don't want I equal to j. It will give us 0 in the denominator. And then I'm just going to add those all up, right? So I multiply it using this symbol here, and then I just add them all up and return the result. Okay, and the same idea, in this case, I'm gonna go between 1 and 4 because our x data was between 1 and 4, right? I'm gonna pick 400 points between 1 and 4. That'll be the points that I choose for my variable x, and then I'm gonna put those into the function as inputs, right? So x interp, x data, y data, that's what my function takes. And I'm going to go ahead and plot that as well. So again, I'm just plotting my x data and y data, coloring them red with a marker O, and then I'm going to plot my interpolation Lagrange polynomial using a dotted line to plot the function. And I've used scatter and plot. Plot will give us a line to plot, and then scatter will just give us the points. And then I've added some labels and all that. So let's go ahead and check this out. Okay, so in this case, we have our data points. And then this is our Lagrange polynomial that's trying to approximate these data points. So we have the 0, 0, what was the next one? 2, 1, 3, 0, 4, 1. And the Lagrange says, well, this is kind of like cubic looking, and it plots something sort of cubic looking. Is that the best one that would approximate those points? We don't know. We'd need more data to start making like good decisions about that. But you get the idea of the general process. Okay, let me pause there for a second and see if we have any questions. Just to make sure that. Oh yeah, okay, so Yeah, that's a good question. So this is a Python. I'm using an editor called VS Code. Python is completely free. That's why I'm using it, because uh, maybe you guys have ways to get different things for free, but I don't. So I use free open source software, Python. And to get this, you can just download them online. So you can just download Python onto your computer, and then if you so let me just yeah, if you download Python, right, and then you can download editor called VS Code, and that's what I'm using to do these lessons, and all of the code in is just something called VS Code. But you don't have to use Python, and all of this code I'm writing, you can easily just write it down in some notation, or just write down the algorithm that I'll send you after class, and you can do the code in any programming language that you like. You could do it in R, you could do it in MATLAB, whatever you want. But yeah, just for this, I'm using Python because it makes for nice lectures, and I could put the codes right in those cells. So it just makes it easier to teach with, and it's free, open source. And I thought, if you guys want to use Python, it's free, open source, so there's no issues there. Yeah, it's a good question. Okay, yeah. So Ha said that she's already sent the material, so you should be seeing that in your box. Just be on the lookout for that. All right, let's go ahead and continue. Okay, some of this is reiterating again, but that's okay. So we'll start going through this. This is the intro. Well, you know what? Before I start this, let's go ahead and take our break, because I don't want to stop in the middle. So let's go ahead and do like a 10-minute break, and then we'll get into the Newton interpolation. So go ahead and use the restroom, or get a drink of water, or whatever you need. All right, let's go ahead and get back to our lesson. Okay, so the next interpolation technique that I want to show you is Newton interpolation. This is another method for constructing interpolating polynomials. However, it doesn't use the Lagrange basis functions. It uses something called divided difference tables. And this helps to simplify the process of finding the interpolating polynomial. Okay, so again, I'm just reiterating interpolation. We want to estimate the data points between discrete points. I think we get the idea there. And Newton is just another technique that we can use to do this. So that's the purpose here, is that we have a second technique. All right, so let's go ahead and understand how do we construct the Newton polynomial. So we use these divided difference tables. And we can use this to construct the Newton polynomial. So what it'll be is basically kind of a Taylor series idea, but we'll multiply by factors of the other missing variables. So let me kind of explain that a little better. So let's say we have a set of data points, x0, y0, x1, y1, xn, yn, and we can define this recursively as follows, right? So xi would be yi, right? And then for all I. So that's pretty straightforward. That's, x0 is y0, or f of x0 is y0, f of x1 is y1. But then we define this recursively, right? So if I want to have more than just one variable in here, then I have to use sort of a recursive definition here. So f of x, whatever I'm at, so let's say x0, x1, all the way up to x2, for example, well, then we take the next one, however it was defined in the recursion, and we subtract from that the I plus k minus 1, and then divide by the difference. So these are like kind of like, they a little bit resemble the difference quotients that you learned about in algebra and calculus. I'll give this to you in the lecture notes, and you can kind of go through here. And I think it'll be the best way to understand this will be to play around with some actual problems to do. But this is just a recursive definition, and it's a little bit weird at first when you see it, but it's one of those things that it's better if you do problems using this to really understand it. You can't really understand it just by trying to read it, right? You have to actually do it. It's like, you can't play sports by watching sports. If you want to be good at sports, you have to do it, and math is kind of the same way. Okay, now, so once we have this recursive definition defined, we can calculate the Newton polynomial. Right, and again, this is going to be a function of x. So as you can see, I have x's in several of these terms for this polynomial. So how does it work? Well, I take the initial one, right? So that would be y0, the initial point y0, and then I add the first divided difference here, f of x0, x1, and I multiply that by this factor, basically, right? X minus x0. And then I add the next one, x0, x1, x2, which remember is defined up here by the ones before it. And then I multiply x minus x0, x minus x1, and then this continues. Right, and so maybe if we go through a little bit of code, it'll make a little more sense. I don't know. I think you're going to best understand it when you actually work it out on your own and by hand. Okay, so that's why I didn't go into a lot of really deep things there, because this is really something you need to do on your own. But anyway, we can look at the code and how the algorithm works, and maybe that'll give you some insight. So again, I've imported the math library or the numbers library, NumPy, and then a plotting library so we can see what's going on, because we want to see what the interpolating polynomial looks like with respect to the points. It's the same idea. I have an array of points, 1, 2, 3, 4. That's my x data. My y's are 0, 1, 0, 1. So it's the same one that we saw previously, but we're going to try doing it by the Newton interpolation this time, just to see if it's different or any better or any worse. And for the Newton interpolation, I define a function here, and it takes the same inputs, right? We have the variable x. That'll be a list of numbers in between, 1 and 4 in this case. And then it takes the x data and the y data as inputs. So we start with an n, which is the length of our x data or our y data. And then we create a basically like an empty vector of zeros that will fill in with the terms of the Newton interpolation polynomial. Okay, so then yeah, the same kind of idea here is that I'm doing the interpolating here recursively, multiplying it by the ordered pair that I have, x minus the data, and then adding all those terms together for my p. And then the same thing here, we have 400 points between 1 and 4. We plug those into the function, and then we just plot the graph and see what that looks like. So I'll have the scatter plot of the points, and then I'll have the Newton interpolation polynomial that we're using. So let's go ahead and look at that. All right, so this one doesn't do as great as as the other one. Yeah, it's 0, 1, 0, 2, 1, and then it completely misses these here. So this one is not quite as good as the other one in this situation. But you can see that we're getting the same sort of polynomial to approximate the points. There might be something messed up here, actually, now I'm looking at this. But anyway. So another example, the same idea for the squaring function. And then again, it misses the point here. It should hit that point, so I think there's some issue in the code here. I'd have to debug it a little bit. So what I'll do is for next time, I'll make a note and I'll put a different algorithm in there, because I think that I might have forgot to add something here. But you get the idea, and the algorithm is completely good here in the notes. It's just that maybe I missed something in the code, but whatever. I apologize for that. But I'll fix that for the next lesson. Okay, so let's move on. Let's see if we have any questions. See how that's going. All right, doing so far so good. So let's move on to our next approximation method. And this is a way to fit a curve to a function or a set of data points. And this is called least squares approximation. And this is a pretty common technique. It's one of the first things you might learn in a statistics class or any kind of theory of approximations. And it's really, really useful. It's been around for hundreds of years, and it's been used to do lots of really great things. So let's talk about this. So this is approximations used to find the best fitting curve or function to a given set of data points. And as an introduction, we want to minimize the sum of squares of the differences between the data points and the approximation function. So we have our data points and we have our approximating function, and what we want to do is take the difference, like, okay, so the function is a little bit off on this data point, there's some error, and what we want to do is minimize that error. And we can minimize that in a lot of different ways, but that's the general idea. And, we'll get into this a little deeper. So see, this is a mathematical technique, and we want to find the best fitting linear or nonlinear model to a given set of data points. And it's really useful when we have noisy data, or when you can see like a linear trend in your X and Y values. So you might choose something like this because you would say, okay, I can maybe approximate this with a line, but there are a nonlinear version, and I'll show you that tonight as well. It's also useful when a simple analytical model doesn't exactly describe the relationship. So you can use this to help describe the relationship between variables when a simple analytical model won't do. All right, and we'll get into the algorithm here too. So like I said, we want to minimize the sum of the squares of the differences between the observed and predicted values. And it's widely used in regression and curve fitting. So this actually has two purposes. It's good for regression and it's good for curve fitting. All right, so how do we build a linear least squares model? Well, this is the linear version. So we want to use this version when we're trying to approximate something linear. And like I said, there's also a nonlinear version. To construct a linear least squares model that fits a given set of data points xi, yi, we want to find coefficients a and b such that the sum of squared residuals is minimized. So the residuals just means the error, right? So we want to minimize the error like we've been talking about in this class from the beginning. And if you look at this notation here, you can see that on the second parentheses here, this axi plus b, well, that's a line, right? What mx plus b, like y equals mx plus b or ax plus b. So that's saying we're approximating the yi's by something linear. We're squaring that, and then we want to minimize this error. And you can see that this is exactly the thing what we want to do to minimize. And how do we minimize that? Well, you remember that you can use calculus to minimize, or you can use numerical optimization methods. There's, like Bayesian techniques. There's all sorts of different ways that you can minimize these two variables. But the idea is this could be a function of a and b. You could use calculus techniques to find when the derivative is 0. That's one way you could do it. Okay, so if we want to construct a nonlinear least squares model, we can use what's called nonlinear least squares approximation, right? So maybe the relationship is nonlinear. It's not a line, so a line wouldn't be the best thing to approximate this y here, right? And same idea, we want to find parameters that minimize the sum of the squared residuals in the nonlinear model. And often this will involve using iterative optimization techniques. So we'll talk about that a little bit more as we move forward. But I just want to kind of get your mind wrapped around the basic idea of regular linear least squares. And then we'll get into the nonlinear version. And then the last thing that I want to say about this is one of its use cases, one of the times that you would actually use this quite a bit would be linear regression. And linear regression is a specific application of this, but it's often when you would use this. But like I said, there's other times you would use this, but you could see this coming up a lot in linear. And it's used when the model relationship between the dependent variable and one or maybe many independent variables, which if you're not familiar with that terminology, it just means that the relationship between the y's and the x's. And then we want to find the best fit line, or if there's more than one variable, it could be a plane, right? Or some higher dimensional object that minimizes the sum of the squared errors. So it doesn't have to be a line. It can be a plane. It could be a plane in 3 dimensions, whatever, but it has to be some kind of linear object. And what that really means is, if you remember from your linear algebra class, it just means like like a vector space, right? Dimension 1 type of thing. So dimension in terms of not the basis of the vector space, but in terms of its sort of like topological dimension. Okay, so let's get into this a little bit, and we'll see how this works. So for this one, I'm going to use the NumPy library as usual for my numerical calculations, a plotting library so we can see the linear regression happening. And then I'm going to use actual linear regression here instead of, in this case, I won't code it all out because I think it's pretty straightforward to see how this works. And it will be a good exercise for you to code this out on your own and then think of some ways you can minimize this. So I'm not going to give all the fun away. All right, so I've collected some sample data points here. I've got my X data, which is just 1, 2, 3, 4, 5, and then I've got some Y data, which is 1.1, 3.5, 8.2, 16.5, and 27.6. And what you can see, there's a slightly sort of monotonic or something linear is kind of happening, or at least, you know, as the X values go up, the Y values go up. So that's maybe a good place to kind of start with your looking at a linear regression or a least squares technique. Now, because I'm using this linear regression imported from the scikit-learn library, right, I need to have the X data in a certain shape. I can't just have a list, and that's all this piece of code's doing here. It's just reshaping the data so that I can use it with this function, because the function takes a certain, you know, shape of data. I make an instance of the linear regression model, and then I fit my model. And all I'm doing is fitting. When I say to fit my model, is I'm just taking this, the sum of squares here, and I'm minimizing this error. When I get the minimum error, then I'll say, okay, this is the best model we have to approximate this function. All right, so I go ahead and fit my model, and then I make predictions using the X data to get wherever my Y values are, which would be, you know, in the previous case, it would be like our interpolation values. For this case, it's going to try to interpolate the best linear regression that we have, the best fitting line to our data is the idea. And then I'll just plot it. Same idea, we have our scatter, which will just be the actual points. Those will be our data points that we had, and we'll call those red. I give it a circle marker, and then I'll plot the X data and the predictions, right? And this will be our linear regression in the dotted line. So one will be just a scatter plot of points. The other will be a line plot or a curve plot of a dotted line. X label, Y label, a legend to tell us, you know, what's what. And then in legend, of course, we'll go with these labels. Those go together. This is a linear regression problem. I'll turn the grid on, and this just shows the picture down in the display below. And then the other thing I've added here is to print the coefficients of the linear regression model. So the slope, or A, will be the coefficient, the first coefficient. The intercept, or B, would be the second coefficient. And I just wanted to add this to show you that, you know, I'm using this model that I brought in from this specific library to do linear regression, and then it'll actually find the best A and B that we have here using the techniques in the model. And if we were using multiple variables, we wouldn't just have a X plus B. We would have also A1, X1, A2, X2. So we would have lots of these, and then there would be an intercept at the end of the model too. And so in that case, you know, it would be something similar to like a neural network, where you have the weights that you're trying to optimize, and then you have a intercept for each layer of the neural network. So you wouldn't be using linear regression in particular, but the idea is the same, that you're trying to optimize those slopes and that intercept. So All right, so let's go and run this and see what it looks like. Okay, so this is a pretty standard linear regression problem that you might see. So how did it work? We had our points in red here, and in that case, I only had like 5 points that I showed you. And we saw that they weren't exactly linear, but they sort of have an increasing pattern to them. So as the x values go up, the y values go up. And the linear regression says, well, I'm going to try to find a line that fits all of those the best. And all of that optimization procedure and everything happens. And this is the best line that it could find to fit these points. So if I wanted to say, you know, what's the value, what do I predict the value of this will be at 4.5, right? Well, then we could use this line to give us a prediction. And then the error of the least squares would give us a little bit of control on the error. So by using this, it's the same idea. We can do an interpolating technique and then get some predictions from that by using this polynomial or line that we found to interpolate. And then finally, we have the linear regression coefficients. And, you know, that's the A and the B. So that's just the slope and then the y-intercept of this line. Right, so negative 8.42, you can see that if this line kept going, you know, the scale, it maybe would hit somewhere around there. And then the slope is positive slope. So you can see that it's a, you know, increasing line, and the slope is about 6.6. So that's why I've printed those out to just kind of help you understand that this is a line, you know, y equals ax plus b. And we're using it to try to approximate where these points would be if we just looked for values that we don't have data for. That's the whole idea here. All right, so that's linear. Let me stop for 1 second before we get to nonlinear, just to see if we have anything. Okay. All right, we're doing good. We don't have any questions, I guess. That's fine. Okay, so that was for lines, you know, when we have a linear relationship in our data. Well, what happens if we're wanting to estimate something for a nonlinear type of thing? Well, that's where nonlinear least squares comes in. So that's what we'll talk about here. Nonlinear least squares approximation is a powerful technique used to estimate the parameters of a nonlinear model that best fits a set of data points. So when is it useful? Well, it's useful when the relationship between variables is nonlinear and can't be described by a line or a linear model or a plane or something, right? So we're going to explore the concept of nonlinear, and then I'll show you how to type that up in Python as well. All right, nonlinear least squares is an optimization technique used to find the parameters of a nonlinear model that minimize the sum of the squared residuals as before between the observed data points and the predictions of the model. Okay, so I have this sentence here about the objective function, right? The objective function is just like the thing that we want to minimize. Sometimes it's called the loss function. And basically, it is usually some kind of an error, and we want to minimize that error with respect to the parameters of our model, right? And it looks something like this. We'll take the sum over the differences between the actual values, the yi's, and then whatever this f is our predictions, right? So in the case before, f was, you know, axi plus b, where a and b were the parameters, and xi was the variable. In this case, we don't have something easy like that. We have a prediction function f, which is a function of xi, the x and the y's go together, but it's also a function of some other variable theta, which we see here. And theta are just all the parameters of the function, right? So we want to minimize this error here. The actual value yi minus whatever predicted value we have from xi and theta. We square that, we want to minimize this sum. So that's our objective function we want to minimize. In this sum, n is the number of data points. So x0, y0, x1, y1, all the way up to xn, yn, as we saw on the very start of this interpolation stuff. Yi is the observed data point, or the f of xi is the, well, that's not good to say that, but it's the function value for the xi's. And then f of xi comma theta is a prediction of the nonlinear model with parameters theta, right? So you can kind of think of this as the xi is the input here, but we also have some parameters for the model. And you might have lots of different types of parametric models. If it's a line or a plane, then it's just the intercepts and the slopes. But it could be something way different than that. So just keep in mind that there could be a lot of different types of functions here. And then, as I said, theta is a vector of model parameters to be estimated, right? So we want to find the optimal model parameter theta that minimizes this expression here. And like I said, there's lots of different techniques we can use for that. We can use calculus. We can use numerical method optimization techniques, all kinds of stuff. However, the optimization process, the point is to find values of theta that minimize this function. So we want to find the right values for theta that makes this as small as possible. And that's the whole idea here. Okay, so to do this, to do a nonlinear least squares approximation, we need to define a nonlinear model function, right? F of x theta, that describes the relationship between the independent variable and the dependent variable, x and y respectively. So before, the model function was ax plus b, and that was describing the fact that there's a linear relationship between the independent variable x and the dependent variable y, right? So now we want to describe it in other cases. The choice of our model function depends on the problem we're trying to solve, but some common nonlinear models might be exponential, logistic, and polynomial, right? So in reality, we've already seen a nonlinear example when we were looking at the polynomial interpolations, right? Those aren't always linear. So when we're doing interpolation with a polynomial of degree greater than 1, strictly greater, we know that that is an example of nonlinear interpolation. All right, let's look at an example here. Yeah, a couple examples actually. So this will be our nonlinear least squares. In this situation, I'm going to use a curve fitter to do this, but it's the same idea. The theory is the same behind it. It's just making it a little bit easier to deal with. So I have these data points. I made 1, 2, 3, 4, 5 for my x, and then in the same ones for my y, the 1.1, 3.5, 8.2, 16.5, 27.6. And like the homework problems, you'll some x and y data, and you'll get to play around with this. A lot of the homework stuff you can do by hand. You don't need to like code it up, because I want you to get some of the ideas, and that's going to be the best way to do that. Okay, so the next thing I've done is define a nonlinear model function. So this will be our function that we want to deal with. We want to try to predict, or not necessarily predict, we want to try to interpolate values for this nonlinear function. And this will be, it's just an exponential. It's taking 3 parameters, a, b, and x. So I'm multiplying it by some a, and then I'm taking e to the b times x, right? A, e to the bx. So that's what this function is. And now what I want to do is I want to use this nonlinear least squares curve fitting method to fit to this nonlinear model on the values that I have. So I have my x data, my y data, and I have a model. So this function here takes as input a model and then the x data and the y data for that model. In our case, the model is the exponential, and the exponential takes in values for x and y. And then we want to generate our predictions for the fitted model. That'll be our, what we're trying to do. So that's going to take our nonlinear model, the x data, the parameters that we've defined from our curve fitter, and that's going to be how we're trying to approximate the xy pairs. So I don't know what function this is, the x and the y, right? But I'm going to use the exponential to try to approximate it by fitting the parameters the best I can to this data. Okay, the same way that we used the polynomials before, this is also a nonlinear function, the exponential. Okay, and then again, I'm just going to plot the points. I've got the data points. I've got the nonlinear model. The difference is the data points is just x, y. Then the nonlinear model is x, and then the predictions that we get using the model we defined above. I've defined some labels and a title, and then finally, again, I'm going to use the estimate. I'm going to show the estimated parameters. In this case, they're not the slope and the or the y-intercept. They're going to be what parameters optimize this as our approximation function, right? So if I have a e to the bx, which values of a and b best fit to these points? So hopefully that makes sense. And then I'll print those out as well. So let's see what this looks like. All right, so there we go. This is a nonlinear. You can see that the data points, in this case, the data points do have a pattern that is when x increases, y increases. But when you look at them, you can see there's not going to be a good line that'll fit to those red dots, right? It's going to be off somewhere really bad. So this is a perfect place for the nonlinear least squares approximation. And using that exponential, I got pretty close, right? So we minimized the squares of the differences here. So it would be, you take what was the actual value here in red and then subtract this distance, add that to this distance, we square them, add that. Well, this one looks like 0. However far this actual value was from the approximated value, square that, add that to our tally, and then the same with this, and then we want to minimize that. And when we run it through that whole machine, we get this curve, which is, remember, the curve is AE to the BX, and the optimal A and B that will make that fit these points is about 1.25 and 0.62. So 1.25 e to the 0.62x is this blue curve here, and that's the best approximation we have for these red points. All right. This is, okay, so this is kind of a little comparison thing I did. Yeah, let's just go ahead and go through this. Same idea. We have our x data, we have our y data, and here I've used the linear function, right? So this is the ax plus b. I've defined that there. And then I've got params and nonlinear params, right? So for params, I'm just going to fit the linear model to the data, right? So it fits the using just regular linear least squares. It's attempting to fit to this data, this line. Okay, so yeah, as I said up here, if we tried to fit a line to this, it's probably not going to be super good somewhere. There's probably going to be a big error somewhere in the line. Okay, and then as a comparison, I next define a nonlinear model, which is the same one we defined above. And that's just a e to the bx. And then I'm going to fit the nonlinear model to the data, right? And when I say fit, I just mean that I plug in the model, I plug in the data, and I minimize the sum of the squares of the residuals, right, or the errors. So that's the idea here, is I'm minimizing the sum of the errors squared. So I've got my linear model, I've got my nonlinear model, I've defined the best fitting parameters I have, and then we can look at what this looks like. So for this one, I've done a scatter plot again for the actual data points in red, right, with a circle marker. And then I'm going to plot using these dotted lines, the linear model, on the X data and my parameters, my parameters. And that'll be our linear least squares. And then another element of the plot will be the X data, but for the nonlinear model. So same data for the x-axis, the y values will be the optimized linear model and the optimized nonlinear model, and optimized to fit the data, right? So that's params nonlinear here is my y function, params is my y function for the linear. So this is x, y, x, y. That's the idea here. I've added some labels for the legend here, and the line style, like I said, is dotted. We had an X label, a Y label. The legend will tell us which function is which. Least squares approximation for the title. We'll add some grid lines, and then this final line is just to show what's going on. So let's go ahead and run this and see what happens. All right, here we have it. This is another form of least squares approximation. The data points are in red, as you can see on the graph, and we have the linear least squares, which you can see that's not doing great trying to approximate these data points. There's just no way to fit it to all of these points because they're not linear, right? So we get a pretty big error if you look at the actual value in red here, and then the predicted value on the blue line. We get a pretty big error here, the actual value in red, the predicted value on the blue line. We get a pretty big error here, actual value in red, predicted on blue line. So you can see right away that the blue line linear is not a great approximation, even though these points do have a relationship that says as x increases, y increases. So that's not enough. We need a little more. And so we see the nonlinear least squares does a much better approximation of the data points. So, these gaps between the actual values in red and the predicted value on the orange curve, the gaps are a lot smaller than they are between the actual value in red and the predicted values on the blue curve. So that's the comparison between linear and nonlinear least squares. All right, I think we'll go through cubic splines before we end, but let me just check the chat again, make sure everything's good with you guys. All right, looking good so far. All right, so this will be our final technique. This is pretty good technique. It's pretty important. I've used it in the real world when I've had to do jobs and stuff, so it does come up. And it's really popular in a lot of like computer graphics, 3D animation, anything where you might not have all of the data points for a whole continuous thing, and you want to approximate that thing, whatever it is, using some technique. This is pretty good. And cubic is pretty much the standard. You don't have to use cubic. As we go through this, we'll see why it's called cubic, but there are other ones too. There's different types of splines, but cubic's kind of the most important because it's kind of the one they use the most that I've seen in industry. So it does come up. Cubic splines are a mathematical technique used for piecewise interpolation of data points. So what does that mean? It means that it's not necessarily going to be one function that interpolates all of the data points, like we saw in the polynomial case and the Lagrange case, the Newton case. We're going to try to interpolate piecewise. So that means we can interpolate this piece between these two data points, the next piece between these two, et cetera, et cetera. And these are commonly used in various fields, like I mentioned, computer graphics, numerical analysis, and data smoothing. So it's pretty good. And you can imagine that if you have a way to interpolate your data points with some kind of smoother function, well, that's nice, because if you understand that function and you have an actual formula for it, then you can do some of the things that you learned in calculus, and you get really nice theorems like the intermediate value theorem. And, those are good to add to your collection of tools. Okay, same idea here for interpolation. I'm not going to repeat the definition for the 10th time, but just pointing out that cubic splines are good for interpolation, and they're really useful when you want to create a smooth curve that passes through the data points. So, all right, so here's the most important part for you guys is constructing cubic splines. To construct cubic splines for a given set of data points, xi, yi, we can divide the data into segments and fit a cubic polynomial to each segment. Okay, so that's a little bit strange sounding probably. And what I mean by that is just that, like, we can look at x0, y0, and then we can look at x1, y1, and maybe x2, y2. And then we can fit a cubic spline on those three data points. And then we can go to the next three, x2, y2, x3, y3, x4, y4, and we can fit a cubic polynomial to those, right? So that's the idea between the cubic spline, is that we're fitting these degree 3 or cubic polynomials to each piece and each segment. And here, it's good to know that it has these following properties, okay? So it's continuous at each data point. So that's nice. That's a nice thing to have continuity, but we had that before when we were looking at Lagrange polynomials, for example. The interpolating function goes through the data points in a continuous way. So it's definitely continuous at each data point. But here we have something a little extra because it has continuous first and second derivatives at each data point. And that's going to give us smoothness, right? Having that continuous second derivative is a really big deal. So that helps us out quite a bit in this case. And then it also passes through every data point. So, if we did the code correctly and it looks correct, then we know that it passes through each data point. And the way that we do this is we can index by I again, like we did with the Lagrange basis polynomials, the L sub i's. But here we have S sub I is generally the notation, and that'll have a coefficient AI, and we'll take that to be x minus xi cubed plus bi, that's x minus xi squared, plus ci times x minus xi plus di. So you can see this is just a standard formula for a cubic polynomial. Instead of, ax cubed plus bx squared plus cx plus d, we're using the difference between the variable x and the xi. So notice some things here, that this is a function in x, and the x's show up in each term except for the constant term. It's indexed by I, so each one of these coefficients is also indexed by I. So that's something to think about. And then also it relies on just xi being fixed. So for each xi, yi, we get an si, right? So if there's n, x0, y0, x1, y1, all the way up to xn, yn, we'll get n of these cubic splines that we can use. Okay, and then just as a little comment, the AI, BI, CI, and DI are coefficients that can be determined by solving a system of equations to satisfy the interpolation conditions. So these are the coefficients that we want to find, and we want them to satisfy these conditions, that the function is continuous and has continuous first and second derivatives, right? So if I take the derivative of this, the first derivative, it would be 3ai x minus xi squared times -1, or times 1, I guess. And then, 2bi x minus xi. And then for the last one, it would just be, -c xi. That would be 0. Take the derivative again. It should also be continuous. So we need to pick the AIs and BIs so that these conditions are satisfied. We can find those by solving a system of equations. That's the idea. All right, let's go ahead and look at some code here. I've done a couple examples here to show you what's going on. So again, I'm using the numerical library in Python, NumPy, and to do our numerical calculations and just to build arrays and things like that. I'm using matplotlib.pyplot, so that we can look at these things and the graphs, to see the graphs of the functions and, to plot them. And then I'm going to use this interpolate library that will allow me to use the cubic spline interpolator to illustrate that to you. So the important thing is that you have this technique here. You can solve this by a system of equations. That's not too difficult. But we don't have to code it up every time, so that's good. The X data, again, I'm just going to use the same data as before because I want to kind of compare and contrast some of these techniques and show you some of the error in the techniques. And for the Y data, the same one as before as well. So the spline, what it does is I can give as input the X data and the Y data, and it will create the spline. And the way that it does that is it just solves the system of equations that we get from this equation here, and it finds the best A, B, and C for each piece of the spline that allows us to have all of these conditions satisfied. So that's what we're looking at here. Oh, excuse me. Okay, so next we want to generate the interpolated points. We want to see, what does it look like? What does the function that it's trying to interpolate look like using this X data and Y data that we have? And so we need to generate some points so that we can plot that function. So what I've done is I've looked at the range of my X data, goes from 1 to 5, and I've generated 100 points in that range, and then my Y will be the value of the spline on those points, and then we'll plot that. So I'm going to, same thing I've been doing is I'll have the scatter plot with the X and Y data. We'll label that the data points. It'll be red with a circle marker. And then I'll plot the input of the X that I made, the 100 points between 1 and 5. And then the output for the plot will be the spline taking input the X points we created. And that'll be the spline for the cubic spline for the X and Y data that we have. And I'll make that into a dotted line. We'll give it an X label, a Y label, a legend, which will tell us which one are the data points, which one are the spline. We'll give it a title, turn the grid on, and then we'll show the actual graph. So. Okay, so this is what our spline looks like for the data points that we had. So these are the same data points we had before. just to go back for a second. This was the exponential nonlinear in orange, and then we had the linear in blue. And neither one of those was a great approximation of this, but you can see how good the cubic spline is doing, right? So it goes through every point, and then it gives us a predictor of the values between the points. So if I want to know what happens at 3.5, if I'm guessing from these points what the point at 3.5 might tell me, I can go up to the blue dotted line and look for the value at 3.5, which is between 10 and 15. Now look at this curve for a minute. You can see that it's definitely continuous at each point. There's no sharp corners, or there's no breaks in the curve. There's no discontinuity. So we have satisfied that condition. And if you look at it, it looks like it could easily be, twice differentiable at least, and that the first and second derivatives would be continuous as well. So yeah, it satisfies all the conditions of our cubic spline, and it gives us a way to determine the value of points we don't have. So it gives us the XY pair for 2.5 and maybe like 5.7 or something. So that's a good thing. We can interpolate what happens between these 2 points. Okay, so the next thing I want to do is just kind of illustrate how these are used. You might be given a job where you have to interpolate something in 3 dimensions. So I want to just kind of go through that and show you how a spline can be used. It's just a simple like curve in 3 space. It's not a surface or anything, but it does give the idea of how you might use a spline to interpolate a surface from a bunch of smaller curves. So I just want to illustrate that here. Again, I'm using NumPy as my numbers library, matplotlib, so that we can look at some plots. But in this case, I'm going to use the three-dimensional plot so that we can see a 3-dimensional plot and how splines can be used there. And then I'm going to bring in these interpolators for the spline so that we can see the 3-dimensional. They're just different ones, a little bit different, but it's still the 3D cubic spline. That's the idea here. All right, so I want to generate some sample 3D points. I just have a value t between 0 and 10, and I'm going to grab 100 points. And then I'm going to have 3 variables that rely on t, right? So this is a parameterized surface. This is a sine t, cosine t, and then z is t. So if you're pretty good with geometry and stuff, you probably noticed right away this is a cylinder, right? So if t was 0, I would be in the xy plane. I'd have the unit circle parameter, using this x and y here. And then so I'm getting, as t changes in the z variable, I'm getting a bunch of copies of unit circles, which makes the cylinder, right? As t gets bigger or smaller, I get another plane, and that gives another unit circle. All right, and then I make a couple of variables, t, c, k, and u, and this will be our 3D spline on the data points that I have for x, y, and z. And just setting s equal to 0 here. And then I want to evaluate my spline at new points. So I have to get some new t values because I'm fitting my spline to these 3 functions which depend on t. So I'm going to need t values if I want to have inputs for my spline. And for that, I just generate 500 points between 0 and 10. Right, 0 and 10 was the parameters for t goes from 0 to 10, so that's my bounds, the domain of my parameterized function. And then I just evaluate my spline using the new t points, the 500 new t points, and then the spline preparation here that I created here. And then finally, we just want to plot it. I'm using, the 3D plotter here, so I'm going to add a subplot, and that's why I have the 3D projection here so that we can see it in 3 dimensions. In this case, I'm going to plot my X, Y, and Z with a red circle. The notation is just a little bit different for the 3D projection. Those will be my original points. And then I'll plot my new points, which will be the spline curve. And then I'll set some labels here and show. So let's go ahead and run this code and see. Okay, so there we have these original points. They're kind of close together. That's okay. And they're on this surface here. And then my spline, which is trying to approximate, the surface here, is shown in blue. So that's the actual spline curve that we got. So we only had these points, but now if we wanted to determine, okay, well, what's a value of t for this parameterized surface that I can maybe predict? Well, I would pick a t, and then it would give me a point on this blue curve, and that's going to be my best approximation for the parameterized surface. And, like I said, this is kind of a simple example. It's probably not the greatest example in the world, but it gives you an idea of how you can use these spline curves to approximate 3-dimensional objects as well. And, you can approximate that by looking at the individual curves in the object, or you could do all 3 if you have a parameterized surface like I've shown here. Okay, so that's spline curves. I just want to talk a little bit about, just kind of end the lesson on a few ideas about the theory that we'll get into a little bit later. So there's other different types of approximation techniques. We've seen some. There's numerical approximation. These are great when there's no analytical solution. So that means that maybe there's no closed form function that you can use. Like when you want to find the solutions to a system of linear equations, that's not bad, or polynomials, that's hard, but it's in some cases it's doable. But another way you might want to approximate is using numerical techniques, and we'll get more in that as the class evolves. Another thing we'll look at to sort of extend this approximation theory is approximations in calculus. So today we mostly talked about approximating functions and approximating continuous functions, but we also might want to approximate derivatives and indefinite integrals. And those divided difference functions that we saw from before will come back again. We'll see those again. So, don't feel, if you didn't get that right away, it's fine. We'll look more into that deeper, and I'll write a little bit better code and show you that to you next time too. So we may want to approximate the derivative. We may want to approximate the integral. In fact, approximating the integral is a really good thing to do because it gives us lots of interesting techniques that we can use to approximate them. And these kind of things show up all the time. From the fundamental theorem of calculus, we know that the integral has a lot of nice properties, a little bit better properties than derivatives a lot of times. So that's something that's good to have. And then, of course, error analysis, which is just assessing the quality of our numerical approximations. We've talked about this a little bit in the previous lessons. It'll come up again. Whenever we have a technique to quantify the accuracy of our numerical results, we'll try to use it. So for example, Taylor's remainder theorem is one such technique. We had that to quantify the accuracy of our Taylor series by looking at the truncated series and then determining how well that is approximating a function. So that's something that you need to keep in mind, and that'll help you to better understand error analysis. And then I just wanted to go over a few like things like, why do we care about approximation theory? Has a lot of applications in many different fields. You know, if you're bored or whatever and you plan on working someday as an engineer or as a data scientist, or I don't know, whatever, just know that this stuff really is important. It does come up, and you should know this stuff. You might need to use it. You might be in a meeting where you have to give some ideas, and if you know something, you'll have some ideas to give. In engineering, it shows up in control systems, signal processing, and structural analysis, among other areas. Those were just three that I was thinking of the top of my head. So yeah, you'll use those splines and all kinds of approximations in all of these areas. So it's not just just for fun. It's actually what makes the world go around. Like probably they were using some of this stuff when they designed the classroom that you're sitting in right now, or designed the circuitry for the way the computer's being transmitted. So this is important stuff. If you're more into art and things like that, this, especially the spline stuff, it really shows up a lot in computer graphics. So whenever you want to render an image or model a shape or simulate like a realistic tree in the video games that you might like to play, you're probably looking at splines. When you're looking at some really cool piece of scenery in something like Fortnite or something, it's probably a spline that's making it look so amazing and stuff. So has real applications here. And that's just a little conclusion. But yeah, I just wanted to point that out to you, that this stuff, has a lot of use cases and does come up in real life. So I'll go ahead and stop there for any questions. And yeah, we'll see. All right. If we don't have any questions, then everybody have a good day, and I'll see you next week. I'll send the lecture notes and some practice problems to the co-instructor. And if you want to look at some of this stuff and play around with Python, you can download these libraries that I typed in the chat. If you can't see the chat, it's just Python and VS Code. You can write it down, and you can just Google that and easily download that software on your computer. All right, if there's no more questions, then everybody have a good rest of your day, and I'll see you all next week. Bye.